Hello everyone. So this video has probably gone up a little bit late because this is the third time I've now sat down to try to record this, and because of issues with Windows, things have gone wrong on the previous two attempts. So hopefully this one will work. And so if there's, ever a reason to if there's ever a time that reminds me of why I prefer Linux over Windows, it is right now. So anyways, last time we were talking about interpolation, and we went over Lagrange interpolation, and we started to do this little exercise here of fitting these interpolations to this particular data set here. And we noticed that when we fit to all of the points in our table, we got these kind of weird bumps at the ends here. And those weird bumps clearly are non-physical, right? So if we were trying to use this interpolation to give us something that is hopefully reasonably physically significant, obviously these points here on the end clearly deviate from what we would consider physical. So we need to figure out a better way of going about things. And so when we when we went over and we learned here about interpolation, the thing that we said is that we need to keep it local. So keeping it local will hopefully prevent these sorts of issues, right? So the idea here is to break up our table into different regions or different kind of sub-tables. And we can pick, let's say, instead of just doing all of our data points here, what if we say pick 3 data points and then use those 3 data points to get some polynomial to fit in a particular local region. And so this should work out pretty well. We actually have 9 data points here, so 3 is a rather good number to use when we have 9 data points. So we can create one region here and hopefully find some polynomial that looks, maybe roughly like that. We can call that region 1. Then we can take these 3 data points and hopefully find a polynomial that fits those. Maybe it looks something like that. Since we are picking 3 points, you will remember our interpolating polynomial is going to be a parabola in the end. So we're going to have a parabola here and a parabola there. And so we can call this one region 2. Over here, hopefully we can find some parabola that kind of more or less does this sort of thing. And we can call that our region 3. And then lastly, we can hopefully find a nice kind of wide, shallow parabola who has an arc that we can fit to that, and we can call that region 4. And so in our code, we're going to need to set up some data structure here that we call maybe regions. And so this is going to be an array of arrays. So we're going to be able to access elements like this. And we're going to store in this our 4 different regions. And so in this particular case, what that means is if you look, our region 1 is going to have to be containing the x values there of 0, 25, and 50. And then our region 2, we're going to do 50, 75, and 100. So you can see region 2 and region 1 are both going to use this point in their determination of the polynomials. And this is a good thing. We want this sort of behavior because our interpolation here, the Lagrange interpolation method, will always reproduce the exact value at a data point. And so by including this point in both of these regions, then we ensure that whatever the function is here will exactly transition into this function here. It won't necessarily be a smooth transition, but it will at least meet up at that point. Otherwise, we're going to get some other issues in our plot here. So then region 3, we would do 100, 125, and 150. And region 4 would be 150, 175, and 200. And so that would be the regions. And so we need to set up our code to do this. And the temptation, of course, would be, well, I'm just going to create some arrays that have these sets of points in them, and I'm just going to feed them in, and that's all I'm going to do. But you want your code to be able to do things for you automatically. So in the end, what we should be striving for here is some code that can do a Lagrange interpolation on an arbitrary data set for an arbitrary number of points in each of our quote-unquote regions. And if we do that, then we get code that we don't have to write specifically for a particular problem. So it can save us time in the end. It might be a little bit harder at first, but once you have this code that is very general, that works in any situation, you can simply reuse that code over and over again. So every time that you want to do this kind of interpolation, you've already got the code, so you just have to use that code to analyze a new data set. And that's going to, in the end, save you some time. So we will be looking in to doing this in code, but I thought at first here, we would just do this kind of overview of what it is we're trying to accomplish, because that can be helpful when you sit down to solve a problem with code. You need to have a clear idea of what it is you're trying to do and how you're going to approach it when you get to sit down and write the code. So we've already said, all right, we need to have something that takes our data table here and breaks it up into these regions, right? So we want to think about, well, how can we do that in a very general way, right? So in general, we will have some n data points, let's call it capital N data points, and want to use n per region, right? So the first thing that we're going to need to do is make sure that our code, given this information, can actually take our n data points and determine how many regions we need in total, right? So to do that, it's not always going to simply be take n and divide by this, right? If we did that in this case, here we're saying we're going to use 3 points per region. We have 9 total points. So if you divided 9 by 3, that would tell you you need 3 regions. But it tells you that because that's going to not include the double counting of the points on the boundaries. So instead, our kind of general rule here is that the number of regions should be given by the number of data points divided by n plus 1. Now, I haven't completely tested this, so this might also need to be modified for some other cases. This will work for this case, right? So if we have 9 data points and we want to use 3 per region, then we can see 9 divided by 3, that gives me 3 plus 1 gives me 4. So I've got 4 regions that we need. But we can also kind of just say, well, let's propose some different things. Let's say that we have n is equal to 25, and we still just want to use 3 points per region, okay? So now we've got some number here that's not evenly divisible by 5 or by 3. So we need to see what's going to happen. So 3 is going to go into 25. What is that? 8 times, right? Yeah, 3 times 8 should be 24. So we have 25 divided by 3 in integer math this is going to just give me 8, right? So here we're going to say this is an integer math. So basically we're ignoring the remainder here. And then we would add 1 to that, so that would tell us we need 9 total regions. And then we can actually do a little check here, and we can see if that is the case. So let's just grab some color here, and we're just going to put down 25 points. Right, so there's our 25 points. And so then we can start clumping them into the groups. So we have 1, then we would have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can see that our simple formula that would work in our specific problem isn't going to work in this other problem here. So we need to try to figure out now a way of modifying our little algorithm here that should give us the correct answer in every single case. So again, let's just kind of count these here. So we need 12 total regions in order to solve this particular case and to be able to handle it. Let me make sure that I've drawn this correctly. I think so, yeah. Yeah. So, okay. So let's see what we can do here. So again, we need basically to, let's see, if we've got 8, so that's how many times 3 is going to go into our number of data points. And then we need to get an additional 4 out of this. So we need some formula that's going to do this for us. The thing that we can do is we can notice that after this first region is defined, we've gone basically 2 points over, and then this point is shared, right? So if we go over 2, and then go over 2, and then go over 2, if we continue this all the way down, you would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and then we just have that 1 point, which is going to end up being in that last region without the overlap. So we can propose now, well, maybe we have this formula, right? So we take our number of data points, we divide by the number of points per group minus 1, because this is going to basically be the number of unique points that we've used up in this, or kind of the net shift over. So with this formula, we can see, again, if we do integer math, we get, for the case of n equal 25, little n equal 3, you would have 25 divided by 3 minus 1, and integer math then would just give us 12, because we would have 25 over 2. Obviously, 2 times 12 gives us 24. And in integer math, we just kind of ignore any decimals to our equation. So well, this would give us 12.5. If we do this in integer math, that's just going to give us 12. If we look at the case where we just had 9 data points and we do this again, you would get 9 over 3 minus 1, so that's 9 over 2. And in integer math, that's going to give us a 4. So this general formula seems to be working, and of course you can kind of test it again with using different numbers, and you can kind of draw out these pictures. You can also, once you've implemented this, you can see, does this seem to be working for any arbitrary number, and if not, then you can always go back and try to fix it from there once you get to that testing phase. So now we've got our method of determining the number of regions, and then we're going to need to set up our code to actually take our data points, right? So we have these xi values, and we need to divvy these up. So we need to divide these up into our regions. And this isn't necessarily all that simple, right? So we need to go through each of these data points, and then we need to assign the values in our regions. So we're going to use our number of regions that we need plus our number of data points. So from this kind of information here, you can set up your regions array. Right? So we had this regions array, and we can say that this is going to be some n over n minus 1 dimensional array here, with then the other dimension being n, right? So we need to go into each of those regions, and we need to determine which of our data points are going to go into that particular region. So in order to do this, we're going to want to set up a double for loop, right? So we're going to have one for loop here, which is going to loop over, say, I in regions, in range. And then we're going to go 0 to the length of our regions array. So this is going to pick up that first dimension of this array. And so this will then loop over each of the regions that we've created storage for. Then we're going to have some j here in range 0 to n. And this is going to then allow us to set the value of regions I, j, to one of the values in our table. So we're going to have some x sub I, and we need to then locate the appropriate value in our array. And again, you can try to figure this out by looking at kind of examples that we've illustrated above here. And we can say, well, for each of these xi, right, so I'm going to grab some color here. So like this would be labeled 0, this is 1, 2, 3, 4, and so on. And so let's label a few more of these 6. All right, so we have kind of points in the first 3 regions labeled, right? And we need to figure out some code to put in here that will take things like our iteration variables here and then figure out where exactly those points are in this array. And so the first thing that we can see is for these first 3 points here, if we just put in the value of j, right, because j 0 to n, if n is 3, then this here is going to tell our code to loop over the values of 0, 1, and 2. So in that case, we just need that value of j. But clearly, once we go to the next region, right, so once we go from region 1 to region 2, if we just had 0, 1, 2, that's just going to give me back these points again, right? So we need something that is going to cause a shift in our values. And the shift is that we need this for region 2 to start at point 2, right? This point here that is labeled 2, the third point in our table. And so we need to have some offset here. And so if we use this value of I, right, so I is going to start at 0, so we can take the I and we can multiply it by anything we want. And then in our first region, this term is going to contribute 0. So now we just need to figure out what do we need to multiply this I by. And you'll note that if I put n minus 1 in here, then we have in our specific example up here, this will be 3 minus 1, that gives me 2. And so when we go to region 2, so we go 0, 1, 2 for region 1. When we go back, and so now I becomes 1, j goes back to 0 because we've gone through this loop once. So then you have 0, we have a 1 here, and this will give me 2, so I'm starting at 2, and then I'll go to 3 because I'll have 2 plus 1, and then 4 because I have 2 plus 2, and so on and so forth. So this will then fill all of these different regions. And I know this seems kind of like we're doing a lot of work here, but again, we're trying to develop this code to be as general as possible. And at this point, we are just about there. We're almost done, okay? So now that we have all of the regions and we have them divvied up, all the points, you know, we figured out the number, which points go in which one. So now we need to find the region that the x value, where we want to evaluate the function, where we want to get a value, we want an interpolated value, that's this position x. We need to find the region that x falls into, because that's going to determine then which of these regions we have we actually need to be concerned about. So we can try to figure this out, and again, the easiest way is just going to be to do, let me write this in that magenta color, and I erased too much. Okay. So we can set up a for loop here, so we can say for I in range 0 to len regions. Right, so this is going to loop over each of the arrays that we put into our regions variable. It's just going to go over that outer portion. But then this would let me set up some if statement here, where I can say, well, if my x value is greater than or equal to this regions I and 0, then we can have, and it's also less than or equal to regions I n minus 1. We want to keep things general here. N minus 1. Then I can set some variable, maybe out here I write that I'm going to have this region, I'm going to set it equal to 0, then I just say region equals I. So if our data point, if the point that we are interested in falls and satisfies these conditions, then we can locate the region that we need to use, right? So this will then find the region we need, and then from here our interpolation is actually going to be pretty much exactly what we did before, but instead of feeding our algorithm the full number of xi points, we're just going to feed the points in this particular region into the rest of our algorithm. So at this point, I will switch things over here on my end, and we will take a look at some code to actually perform the interpolation using our modifications. All right, so now let's take a look at implementing some of the changes we were just discussing in our actual code. So these are the code files that we put together last time. We have our code that actually contains the resonant cross-section data and then has where we called our interpolation function and created a little plot for us. And I don't remember if I had this in there during the lecture last time, but this just kind of refines that kind of peak position that we would estimate. And so we can rerun this code just to remind ourselves of what the output looks like. So we get our peak position a little bit more refined than what we got before, and we see it does appear to be kind of slightly before that data point there according to this particular interpolation polynomial. But we can see, we clearly have these kind of non-physical behaviors, and we're hoping that we can get away from those and actually end up with some code that will be a bit more general and solve a bit more general of a problem. So the first thing that I'm going to do is I'm going to start modifying my interp.py code here. So this contains my interpolating functions that we've written so far. So just the one Lagrange interpolation and its helper function here, this lambda I. And so we're going to use NumPy to basically help us set up our arrays so that we don't have to worry about the using, say, the Python lists, which have some shortcomings that would make them a bit more awkward to set up. Hang on, just pulling up my notes here that we just went over. All right. Okay. So the first thing that we're going to want to do is set up a variable now inside our interpolations to store those different regions, right? So we have our regions variable, and we're going to say that this is a NumPy ND array, where the ND is for n dimensional. So this is kind of telling our code here that this is some arbitrary dimensional object that we want to create here. And so I want, again, to do integer math like we were saying before, and we want this, again, we figured that this should be my number of data points, which we can get basically by taking the length of any either of these two arrays, really, because those in principle should be the exact same length, because it's just the dependent and the independent variables. So we take that length, and then we are going to divide this by our n minus 1, and that should give us then the dimensionality of that first part of the array. And then the second dimension is just purely going to be n. So we can pass that to our shape parameter, and then this will just create an empty array with all of that, with the proper dimensions that we want. So now, once we've created that array, then here we're going to go into our loops where we want to fill that array, right? So we can go from 0 to len regions. Again, that's just going to pick up that first dimension of that array. And then we want to go j in range 0 to n. And then we need to set the values, right? So this is just filling our regions with the appropriate values. And here we said that this should be the x value located at I times our n minus 1, so our number of points per region minus 1 plus j. And that should give us the appropriate values stored in each of those regions. And then again, now we're going to locate the specific region, and then we're going to loop over things here. So we're going to create that region variable, and again, we're going to loop over all of our different regions and just find the one that happens to contain our particular point. So if x is greater than or equal to regions I 0 and x less than or equal to regions I n minus 1. So basically we're just taking that very first point in the region, and really we should probably set this up so that one of these is just either this is just less than or this is greater than. But I guess no, I guess we'll leave it on both. It doesn't really matter. So my thinking there, right, my little hesitation there was just that you don't necessarily want a point to evaluate as in two different regions, but the points where that's going to happen are going to be the specific endpoints, and it doesn't really matter which of the functions you use for your endpoints because they should both return the value at that data point because it's an actual data point. So in the end, it won't actually matter whether you do less than or less than equal to. But the reason I ended up keeping this was I was then thinking, well, if you get to endpoints, you may run into a problem if you don't have that equal to condition, right? So we're going to keep that on both, and it will just end up picking the higher of the two regions for some of those boundary points. But again, it doesn't, in the end, actually matter for those. All right, so now we're still going to have this code exactly, this for loop is going to stay exactly the same. We're still just looping over n total points. It's just that now n doesn't have to be 9. It doesn't have to be all of the data points. We can have it be some subsection of data points. So we can have our different values of n. We're still going to be evaluating this lambda function, but now instead of passing the xi, we're going to pass the particular region that we are looking at. So we're going to take the region that we located up here. We are going to use that and pass those particular points to our lambda function to get the value of the lambda given our x. So that's the only change to that line. But of course, we also need to change this here, right? We need to figure out which particular point we are talking about here, right? So this I is going to pick one of these particular points in our region, and then we have to do some calculation at each of those points. And so down here, we need to get the correct value from our G of I array. Now we could have also created another array up here where we divvied up these points into that array, but we can also instead create this little variable here. I'm just going to call this IDX, so just for an index, and this is just going to find the index in our xi array where the particular value in our region happens to fall that we're currently considering. And again, we're going to make use of some numpy functions here. So there's this numpy function called arg_where. So this is for the argument where. So this will return the index of an array where some condition is true. And so I'm going to take all of my points in this xi, and I'm going to say where that is equal to regions, then the particular region, and then the particular value. So I'm just going to be locating this particular value in my xi array and returning the index of that value. We do have to be careful here. The reason I wrap this in an integer is that this function isn't necessarily going to return an integer, but when we go to plug in the value down here, right, so now instead of I there, I'm going to have this IDX. This has to be an integer value. So now we've modified our code. We can see it's gotten a little bit longer, but not too much, right? So we didn't add a ton of code, and yet we've made it much more general, and hopefully it will produce a better result. So now we can change these here over to, say, 3, and then we can run our code again, and we can see no longer do we have these huge bumps at the endpoints of our data. It's still not great, right? So you have this kind of increasing function here, and that's because, again, we're taking a parabola to fit through those points. And up here, things seem to be okay. And we get now that this peak location is actually a bit higher. So let me make this a little bit bigger here. Let's just do that. So we can see now that we're no longer using a kind of global fit. We get this shift, and the peak is now actually past that data point. And if you look in the textbook, I believe they tell you that from better data and a more in-depth analysis, the peak location ends up being somewhere around 78. So we've gotten closer to the actual result by switching the way that we are doing our interpolation. Now, again, it is still not perfect, right? It's not a great representation because we can see it is kind of subtle, but if you look in very, very closely at particular data points, at those boundary data points, you can see it is not a smooth transition between these. So the values match on to one another, which is a desirable feature, and we want to make sure that is the case. But this is not necessarily desirable to have these non-smooth transitions. And you can also see over here, again, we also have this kind of artificial sort of dip and then rise in our data, and we have an artificial dip over here. So we've improved things some, but not as good as they could potentially be. And this is then going to lead us into our next topic of discussion. And this will probably get posted as a separate video because I need to edit this one, get it posted, and try to get it linked up onto Canvas. But the idea that we're going to explore next is called cubic splines. And cubic splines, as their name implies, are going to use third-order functions in different regions. And they're actually then set up so that not only do we get the values matching at the boundaries of the regions, but they also match smoothly. So we have this condition of the functions being equal at the boundaries and also their derivatives being equal at the boundaries, so that we get this nice smooth transition from one region to the next. And so this produces very, very good looks in the end. Okay, so I am going to quickly show you just what a cubic spline would look like fitting to this data before we actually describe creating them. So first, let me just list, so I have my file names there. Then we're going to launch GNU plot. And so I'm just going to do a very quick, simple plot here. So I have this file res.dat that's containing the data points, so that has these values in it there. So we're going to plot that using columns 1 and 2 with no title, with points, point type 7. And then we are also going to plot this other file here, this one. So that this is these are the files that I was using to create the plot that we had in our lecture, where we were just kind of discussing things. 1, 2, no title with lines. We'll make that a little thicker as well. And so then the last thing that I'm going to do here is I'm going to replot this res.dat, again using 1, 2, with no title. And this time I'm going to say smooth C-splines with lines. And so this is going to have GNU plot actually create these cubic splines to fit between all of those data points. And so then we can take a look. Let me redo this, make that line a bit thicker so that things are easier to see. Okay. And again, I'll make this plot a bit bigger so that it's easier to see. And so let's make this again look a little bit bigger, a little bit better. All right, so that just smooths things out a bit. So you can see here that the light blue line, that's going to be the cubic spline. And so we'll learn how to create that function to do that sort of splining. And so we have this point here, sorry, this green curve. So that was our original implementation of the Lagrange interpolation. We did improve that a bit, but we can see here that the cubic spline gives us this kind of nice, smooth looking function. We get a lot less kind of weird behavior. You don't have this artificial dip over here or over here, and everything is nice and smooth. So the goal then of cubic splines is to basically provide us with a much better way of interpolating values. So I'm going to end this video here, and I will get this posted onto YouTube and everything. I've got a little bit of editing to do first, and then hopefully in not too long after I get this one posted, I can get a discussion of those cubic splines posted as well. So until then.